until last class, in our previous lectures, we have studied several methods of voltage measurement, including peak voltage measurement using sphere gaps also we have studied earlier. In this lecture, we will study simple peak reading meters, the Chebb and Fortescue method. Let us see what it is. Why do we need peak reading meters? What is important for testing of power equipment? Whether it is RMS value, whether it is average value or peak value. I am asking this question to you. Which is important for testing of any power equipment? Peak value or RMS value or average value? The peak value is believed to normally initiate the breakdown generally. So therefore, the instantaneous maximum field or instantaneous maximum voltage generally believed to be causing breakdown. So therefore, it is important to measure. And for DC fields, however, standards will specify ripple limit less than 3% or so. So by that, if you measure average value, it is sufficient for DC fields. But for AC and impulse fields, the peak voltage need to be measured. What is exact peak that is occurring, that is appearing on the test equipment need to be measured accurately. Why do we need peak reading meters? Whether sphere gaps etc. are not sufficient. Until now we have studied them, right? So spark gaps or sphere gaps can measure peak values of all types of waveforms, AC, DC, impulse or any other arbitrary waveform. Spark gaps can be used to measure the peak voltage because the breakdown in the gap breaks due to that peak voltage. So you can measure the peak voltages using spark gaps. But they need calibration and then factors, various factors, correction factors to atmosphere, and then lookup tables, and then it is a cumbersome procedure, and they have at the same time limited accuracy. Accuracy is not 100%. So this aspect is hindering its application in day-to-day applications actually. So we need more convenient methods to measure the peak voltage. Of course, they will be used for calibration. For day-to-day measurements, we don't need cumbersome procedures like that. So peak voltmeters are needed. So what about generating voltmeters? Generating voltmeters can also work for AC, but the voltage is higher than 100 kilovolts, the design becomes complex and cost increases. Cost of building for stable electric fields at the sensory electrodes increases rapidly. So until 100 kilovolts, generating voltmeters can be used for AC. But beyond that, we need additional cost to be incurred for making them. So this is the problem with generating voltmeters. And resistive dividers also we have seen what are the limitations. They are also limited to around 100 to 200 kV due to limiting currents and heating effects and then stray effects of capacitors etc. So we limit normally to 100 to 200 kilovolts. So for high voltages, even higher than that, then we do need peak reading meters. So why not measure indirectly? See, we have seen how high AC voltages are generated and how high impulse voltages are generated. We have seen right earlier in generation. So in that, can't we estimate the voltage at the output using the input voltage? For example, AC, there is a cascaded transformer set, right? Or you have resonating transformer also. Can't we measure the high voltage side voltage using measurement at low voltage side? Is it not possible? Okay, exact value is not up. Why exact value is not possible? Can someone guess? Why is it not occurring exact value? Due to? No, not due to calibration. Not due.
We are using these transformers into the picture. The inductance to take a certain effects of the transformer also come into play.
Yeah, exactly. See, no load voltage and voltage when load is connected is different, right? We have studied that also, and even resonance also we have studied due to that, right? So, actual voltage applied across the test object is not same as the value calculated using turns ratio.
Yes, sir.
Because of internal impedance of the transformer itself, as well as the impedance of the load itself, and then connecting lead resistance will also come into picture. Of course, that is small. So, due to these effects, the output voltage is not exactly same as input voltage multiplied by turns ratio. Therefore, we cannot do indirect measurements in this case, AC case. But what about impulse case? Can we estimate the impulse peak voltage using input? What was the input to impulse generator? What are we doing fundamentally? What were you doing when we studied? Impulse generator works basically by charging the capacitors in series and then connecting them in parallel, right? Basically, a capacitor is equivalent if you assume a capacitor is charged, right? So, based on the voltage of the capacitor, the charged voltage of the capacitor, is it possible to estimate the voltage peak? Given the values of capacitances and resistors connected. So you have formula, right? Double exponential formula. Using that you can estimate impulse voltage peak also you can estimate. But whether that will remain same always. For example, always I charge the capacitor to a particular voltage V1, and always can I get V2, which is the peak voltage on the impulse? Is it always possible, or here also some effects will be there? Anyone speaking? I cannot listen to anyone. Hello?
Sir, the capacitors we can't be sure will be charged always to the same value, right, sir?
Suppose we have assured and then we know the exact charging voltage of the capacitor. It is possible, it's not so difficult. Those are input capacitors only. They can be charged and the charged voltage can be measured. But the problem here is again, when you are connecting a test object means test objects will change, right? Test object will also have certain capacitance, and then the output gets modified according to that value of the capacitance of the test object. Therefore, it is not always possible to estimate accurately what is the impulse peak also, based on the charging capacitor voltage. So, therefore, the indirect methods of measurements will fail. So, directly we have to measure the peak of the output voltage. So, for that how we will do? So, this is the one of the methods known as Chebb and Fortescue method. These two are inventors of this circuit. Now, how this circuit will look like, I will draw here. It is a simple capacitor with anti-parallel diodes connected like this. Now, I am drawing fundamental circuit only. Some improvements have to be done, that we will discuss after a few minutes. So, there is a diode here, and then this is an ammeter. And this other diode is connected anti-parallel to the first diode. So, this is the circuit. So, voltage V is applied here. So, what will be the current here through this capacitor I? What happened? Huge noise is coming. Can you repeat that, whoever have spoken just now? Can you please repeat? Ravi Ranjan, what is the capacitor? What is the current through this?
Sir, the applied voltage is DC or AC?
You can think in general, na? You see, if you apply DC voltage to a capacitor, will you get any current after some time? So, it is time varying voltage.
C dV by dt. Sir, DC current will get.
Huh?
DC current.
DC current. This voltage is, assume that it is a time varying voltage.
So, current I of t is equal to C dV by dt.
I equals to C dV by dt. Right? Now, why is this like that? Why is it like that? This is simple capacitor, right? So, one diode is in, upward direction, other is in downward direction. So, always there is a connection to the ground. So, equivalently, this is simple capacitor only, if you ignore the diodes and all. Okay, it's like this. Therefore, I equal to C dV by dt. Neglecting the drops across the diodes and drops in ammeter. So, this is approximately equivalent to a single capacitor connected to the ground. So, when you apply V, I is equal to C dV by dt. That's what you will get. Now, if this is the case, then what will be the current measured by ammeter? This ammeter is of moving coil type. or average reading meter. So what will be the current read by this ammeter? Zero?
Half cycle will get, so that average of half cycle will get.
Average of half cycle we will get. Right? Everyone, is it clear? Because only positive current will flow through this diode. D1 say. And D2 will pass only negative current. Right? The ammeter is kept only in one of the paths containing the diode. It can be kept in the other path also, with other diode also. So assume it is kept here. It will read the only positive current. What exactly that current is, let us see. Now you remember the circuit, right? It is very simple circuit. I will redraw here. Just one diode downwards, ammeter, and then one diode upwards, then ground. This is V of T I. Right, now I will draw typical waveforms. So pure sinusoidal I have drawn now. Suppose this is the waveform. You can start at any instant. I just started at this instant in order to give you in first half cycle some positive current. So now how the current will be at t is equal to 0. This is T, this is voltage or current, both I am drawing on the same scale, right? Now how the current will be? Let me draw current on a separate. How the current will be?
So sinusoidal.
Sinusoidal, and at t is equal to 0, should it be rising or falling, and what it is?
It should be rising 0. At t equal to 0, it should be 0, and it is rising like the sinusoidal.
It is rising sinusoidally and will reach the peak at t is equal to pi by 2, right? Omega t is equal to pi by 2. So this is the positive half cycle, right? Can you see?
Yes, sir.
Now, if the meter is average reading meter, so it will read this average value, because this diode D1 will conduct during this time, this period. Only D1 we have to consider, because the ammeter is connected only in series with D1. Now, the other portion of the current, D2, I will draw here. This is D2 again. Will be like this. This we are not interested, because this is not going through the meter, and this is not being measured here. Only D1 is the current through the D1 we have to consider. And what is its average value then? This is entire period T, we have to average it out. Right? So this is V max, V max, V plus max, let me say, V plus max. This is V minus max, negative peak and positive peak. If you write the equation for current, I equals to average current, the meter is moving coil type instrument, therefore you have to average it out for one cycle fully, but your diode is conducting for half cycle only, that is 0 to until T by 2 only, right? So this is I of T dt, right? Now I equals to what? C dV by dt, right? So this integration becomes C by T integration of d. Huh? Integration of dV only, and the limits change for voltage limits, right? So voltage limits, what are the voltage limits? V minus max to V plus max, right?
Yes, sir.
Minus max to plus max. This is the limits of this integration. So what it becomes? I equals to 1 by C by T into V plus max minus or minus of minus, right? Then this will be plus again V minus max, mod value you have to add here, like this. You understand? V minus max is negative, right? So V plus max minus of minus V minus max will come. So I am simply writing V plus max in plus V plus max in mod, V minus max in mod. So this if both for pure sinusoidal V plus max and V minus max are same, right?
Yes, sir.
So I equals to C by T into 2 Vm, right? That is maximum voltage. So V by T, C by T into 2 Vm, right? This can also be written as 2 C, 1 by T is frequency, 2 C F into V max. So what is happening here? Actually we are measuring peak to peak voltage, right? The average current I is proportional to peak voltage, or if the sinusoidal voltage is having both peaks same, it is proportional to peak voltage, right?
Yes, sir.
So peak voltage can be measured using this system. Now I have one concern here. Let me draw another waveform. I will erase all. Now, suppose my waveform is having a small kink like this. This voltage waveform. Now in this case, how the current will be?
Nothing, sir. At 0, we will get a peak and same follow the graph. 0 at we will get peak and at peak we will get 0 and that kink we will get that kink input. The kink, if kink is showing peak, then we will get downward peak. That follows.
See, if this kink is having positive slope, then the current is
Rising, sir. Positive.
like this, right? In this case, if I integrate, what I will get? Will it be C by T into V max, V plus max, say, V minus max plus mod V minus max, or anything different from this?
Same, sir. Same, sir. Same, sir.
Same. So it can still measure V plus V max minus V max, right? The peak to peak voltage it can still measure.
Yes, sir.
Now, suppose this kink, actually this kink slope alter the situation here in the current. If this kink is attaining a peak and then going down, okay, then what will happen? See here only positive slope is shown here. So let us see one more waveform. Why such waveforms will occur? We will see soon. Now, if the voltage waveform is like this, see there is a false peak here. Is it peak really? No. It is a false peak. After this, the voltage has gone down. Then what will happen to the current? If voltage is going down, what will happen to the current?
Increasing, sir. Rising, sir.
No. Voltage is going down means what? After the peak, voltage is going downwards. So what is the current actually? I is equal to C dV by dt. dV by dt क्या हो रहा है यहाँ पे?
That is negative. Slope is negative.
Slope is negative. So slope is negative means current is instantaneous current is.
So that is also negative.
So at this false peak, the current becomes 0. And after that, the current becomes minus until this another peak, downward peak is there. Na? So during this period, the current becomes 0 and again rises. So the current will be like this, and here it will become negative, and then again it will be like this. Okay, roughly. Now,
Please can you repeat this?
what did you say? I equals to C dV by dt. Okay. Whenever dV by dt is positive, current is positive. Whenever dV by dt is negative, current is negative. dV by dt means what? Slope. Right? Now, from this time to this time, the first instant, this time to this time, whether you can see the arrow? Yeah, now it has come. So, this time to this time, the slope is positive. Voltage slope is positive. Do you agree? Therefore, current is positive. And the slope is becoming from 0. Initially at t is equal to 0, it is 0. Again, at the end of this interval also, it is 0. So, that's why there is a pulse like this during this period. It is starting from 0, ending in 0, and always remains positive during this period. This is the area under that.
So can't we say that the current is rising in negative direction?
Huh?
Can't we look at it as current is rising in negative direction?
Negative direction, negative value of the current, minus only. Rising, it will rise and then again come back now. Because the slope is, if you consider this small interval, at the beginning of the interval, I equals to 0 because the slope is 0. At the end of the interval, again I is equal to 0 because again slope is 0.
Yes, sir.
So, in between, slope is negative, therefore current should be negative. So the small pulse, negative pulse will come in the current, right? And next period, next again from this next interval, again the current is the slope is 0 at the beginning of the interval and 0 at the end of the interval, and in between it is having some positive slope. Therefore, this is again positive. Now, my question is, what is the average value seen by the ammeter?
So one half cycle in downward negative direction for current to go.
See, we have to integrate for half cycle only. That anyway negative, right? This is negative. This anyway negative. Right? This is negative. I stopped here because this negative current we are not interested. The reason is you have to average out for one interval, right? And in one interval, whichever current which flows in through this diode D1, that we need to consider. So we have to average out this to the entire interval. I am not trying for entire interval. So here you observe carefully. Now this is half interval only. This total time is T by 2. This is T by 2. Of course, we have to integrate for entire period, assuming that it is the waveform is repeating. Now you see carefully these two positive portions D1 will conduct. Do you agree?
Yes, sir. Yes, sir.
What about this negative current, this negative pulse? So D2 will conduct, so it will not go through our ammeter. So you cannot average it out. So you cannot consider that in calculating the average value. Am I correct?
Yes.
Now, the measured value, of course, there is some average value here. Okay, there is some average value which is the area under the curve divided by entire duration t. That shaded area. Okay, the shaded area divided by entire duration t if you do, then you will get the average value. Then will it be proportional to, will it be same as c by t into v plus max minus v minus max, sorry, plus of mod of v minus max? Is it same? Is it same, or it is higher, or it is lower than this value?
It is higher than that.
The measured value will be, huh?
It will be same, sir, because we will have to integrate the whole of the voltage area under the voltage wave.
Area under the current, please. It is not voltage. We are averaging out the current. The ammeter is moving coil type which will average the current. Okay. Area under the current curve. Now, since the diode D1 doesn't allow the negative portion, this negative portion we cannot average, cannot consider in the average. Okay. So, the measured value will be higher than the previous value, actual value. The meter will show higher because the negative area we are missing. If we include the negative area, you will get exactly v plus max minus of minus v minus max, or v plus max plus mod of v minus max. Exactly, the meter reading will be proportional to this one, peak to peak voltage. But now what is happening, since the negative area we cannot consider in the averaging out, so the meter will read higher value. Higher value or lower value? Whether the net area under the curve increased or decreased? Huh? Increased because negative portion is missing. If negative portion is included, then you will get exact value. But since negative portion is missing, you will get higher values. So this is one source of error possibility. But the voltages, the testing voltages normally do not include harmonics. Okay, the standards clearly specify that the waveform should be as pure as possible. So these harmonics, in source itself is ruled out. But there are possibilities actually. There are possibilities for this kind of things to happen in testing circuit due to pre-discharges. How those will occur, let us. So this is measuring circuit. This is HV source. We can write maybe SPR. This is HV source, and then the test object. Okay. Now what will happen is, through this path, as the voltage is increasing, so inside the test object there may be certain discharges. So that will cause the voltage to dip. Although you may be supplying pure sinusoidal voltage, that will cause the voltage to dip like this. It may be possible. So to avoid this can be minimized using, by connecting a resistor in series with this damping resistor between test object, and this is test object, and a measuring circuit. This is basically capacitor actually. That's the reason discharges can occur to test object. Pre-discharges, they will, the voltage waveform gets a little bit modified if it is not, controlled by using a damping resistor. So this can be addressed actually by connecting appropriate damping resistor. But if the waveform, if there is a kink with a negative slope in one of the half cycles, then there is possibility of error. This what is studied now. If the current reaches 0 more than once in a half cycle, exactly what we have studied just now. And then the sources of errors. Now the equation for I is what was it? 2 times C F into Vm in general, right? This is the equation. Now, what are the sources of errors? Looking at this, see, you have to measure current accurately, right? So, the current is in milliamperes only. That range is in milliamperes. So, it can be easily measured by moving coil accurately. That is possible. Now, your capacitor should be having accurate value. Actually, for measuring such currents, such voltages, standard capacitors are used, which have very precise capacitance values, which the capacitance can be measured. Standard capacitors with precise capacitance value will only be used. Therefore, C can also be accurate. What about F? Frequency. See, this is the frequency of power system. Normally in testing laboratories, so the frequency will be reasonably accurate. But if there is an error in the frequency, definitely it will introduce errors in this estimation of Vm. So, estimation of Vm depends on all these quantities I by 2CF. So, the errors in I, F and C can introduce the errors in Vm. But normally I can be measured in accurately because it is in milliamperes. Frequency in testing laboratories is more or less accurate, and capacitance, standard capacitors are used. Therefore, this will also be accurate. But there is another problem. These are fine, but due to diodes, some imperfections may be there in the diodes. The reason is, what is the forward current and reverse current expected? Suppose if the reverse current is also significant, then what will happen? Yeah, there will be error, right? Because you are expecting the current to flow through this diode. But if the other diode conducts in reverse direction a little bit current, so to that extent, error will be there. But what is the problem? Reverse currents are small. But here, the ratio of, forward current and reverse current is roughly 10 to the power of 5 to 10 to the power of 6 times. So that makes it difficult. The forward current is so high compared to reverse current. So the expected reverse current. So reverse current should be sufficiently low. That imperfections may occur in case of designing the diodes. Therefore, diodes have to be designed carefully. This is one thing. And then protection. See, what if breakdown occurs? What will happen? Now we have studied only fundamental circuit. Actual circuit does have some protection. So in case of breakdown, what will be happening? Circuit will
start automatically. Means that figure.
Circuit will start automatically means what? Now, what do you mean by circuit will start automatically? Start, you said? Start, na?
Yes, sir, start.
Start means? I am giving.
We are not going to measure any equipment as high voltage potential. High voltage component is far more than actual potential of resistor. Then for shading megaohm. Here load is not connected there. If load is not connected, some distance is between actual potential and
No, breakdown. By breakdown I mean not the breakdown of your measuring circuit, measuring equipment. Breakdown is breakdown of the test object. See, measuring circuit, if breakdown occurs inside, then that design is not good. So don't assume the breakdown inside the measuring device. It is of the test object. If the test object breaks, means there will be short circuit like this. Or indirectly, what I am asking is, if a capacitor is suddenly connected to ground, what will happen? Charged capacitor only, high voltage. So when you are applying high voltage and testing the test object, obviously it is charged capacitor only. Suddenly, if a capacitor is connected to ground, what will happen?
It may explode. The sudden discharge of charges happens, sir.
Sudden discharge of charge will be there. Okay. So an impulse charge will be there. Impulse charge. Right? Or an impulse current you can assume. Very short duration current. Why that will happen actually? Suppose if this plate is charged to plus and minus. So that certain voltage to certain voltage it is charged. And at that instant suddenly breakdown occurs. Then these plus charges have to go through this breakdown channel to the ground here. And the minus charges again, they have to go through this diode to the ground again. Right? Minus charges, I have drawn opposite direction here because current is the opposite to minus flow of minus charges, right? Direction of minus charges. So that's why I have drawn through this diode. So in the charges on the positive plate will go through the test object, and then the charges on the lower plate, if it is negative, and then they go to the ground through this path. This will happen instantaneously in a very short duration. Heavy current will flow, right? Suppose if the high voltage is high voltage is negative, going through the negative half cycle when at the instant of breakdown, then these charges will be negative, minus. and these charges will be plus, 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 plus. So in this case, the current will go here in this direction, opposite direction. But in this case, through this diode it will go at the instant of breakdown. So it will go through the meter in that case, right? So depending on the voltage of the capacitor at the instant of breakdown, the currents can flow through the either of the diodes, and if it is very short duration high current, that may damage the diodes, right? Or it may damage the ammeter also if it is the impulse current is huge. Normally short duration, right, it will be huge only. So entire this thing is happening because of the HV plate is getting connected to the ground. Now how to protect in this case?
So connecting and across and spare gap, sir. Not talking of spectrum.
Connecting across test object and sphere gap. Why suddenly sphere gap you have brought into picture? Measuring and test object. There is a resistor, of course, protection. Even then, when you are directly shorting this, test object, sudden discharge is expected from the capacitor. So, how to protect? See, what are the things that need to be protected here? The two diodes and ammeter need to be protected. Can you suggest a way? That protection should be against high currents, not high voltages. See, high sudden current is going through the diodes in case of breakdown. Therefore, the diodes have to be protected, and then ammeter has to be protected for this sudden pulse current. Right? How is it done? So let me draw the. No. Inductor will complicate the matter again. The current will be different, right? Inductor if you connect. A small protecting resistor will be connected like this. The protecting resistor, will it limit the current? Okay, I have drawn the diode in opposite direction. It doesn't matter. Opposite means opposite to what we have discussed until now. It can be in either direction. This is grounded. Now, here, protective device is connected like this. See, I could not draw ground at this middle portion, that's why I have drawn here. So don't think that it is a modification. It's not a modification. You can assume ground at this position itself. The pen is not working here, that's why I have drawn. Now, how this works? This is a protective device which can be even simple air gap also. But it can be a Zener which breaks at a particular voltage. So this is, if the voltage crosses certain value VBD of this gap, then it will make it 0. Right? This is a resistor R. Then how it will protect, high current, if this protective device is not there, this protective device is not there, by simple resistor, we cannot control the currents properly. The current magnitude, only little bit it will be affected. So, what is done here is, so the resistor other end, this end, you can assume it at ground potential only. But at this end, so the moment current rises, the suppose impulse current is I into R. That voltage is generated at this node. This is impulse current, please. I is impulse current I am talking about. At the instant of breakdown, for the small duration, certain impulse current, if you assume I into R, that voltage is generated at this node. If the voltage is excessive, if it is more than VBD, then this gap will break, and then this node voltage is made 0. It will directly connect to the ground. This is directly connected to the ground. So then what will happen actually? It doesn't allow the current to rise beyond certain value. What is that value? I max equals to VBD of the protective device divided by R. So this is the maximum, this should be the maximum impulse current that is allowed through the diodes or the ammeter. Did you understand how to design this resistor? So this is the way. So this I, whatever I am talking about, is impulse current. If I is the impulse current magnitude, VBD, what is VBD? VBD is the breakdown voltage of this protective device, and R is the connecting resistor here. So if you use these values appropriately, you can limit the maximum current I during the breakdown. So this is how the protection is ensured in this case. Anything?
What if the test object breaks before that air gap we have provided as productive equipment?
What is the?
Because what in case the test object breaks down before that protective equipment?
Before that protective equipment means what?
I suppose that it breaks down before VBD. The test object breaks down before the top capacitor voltage reaches VBD.
No. Test object, see, we are not bothered about if test object fails, that is the problem of test object. But if we have, if our voltage is such that our current is not increased beyond I, our meter is protected, irrespective of whatever happens to test object. You have to design your R in such a way that this I is limited. That's it. The I through this will be limited to this value, whatever VBD we are designing, and then R we are designing. Test object kuch bhi ho, it doesn't matter to us.
So there are two resistors in this system. One for test object to limit the current, and second for measuring instrument for getting a voltage.
Exactly. That high resistance, that is connected between the measuring instrument and test object, that will not protect my diodes, right? So this resistance that is connected inside this one, this is especially to protect the diodes and ammeter. Okay. So I think I have covered protection also. Yeah, so this is about this method, Chebb and Fortescue method. Do you have any further questions on this?
You said that impulse voltage measurement of impulse voltage when the load is connected, then load capacitance also taken in account and create a problem.
Measuring
of impulse voltage testing, sir. Impulse voltage testing. In impulse voltage.
impulse voltage testing. Yeah.
Load is connected. Load has also some capacitance.
Yes.
Then it causes an error in measurement, sir.
Yes.
And I'm saying that if
that is if you measure the voltage by estimating the charging voltage of the capacitors that are charged. If you analytically estimate, errors will be there. But if you directly measure, there will be no error. You are measuring directly, right? This is direct measurement. Directly you are connecting to the terminal of test object and then measuring. So in this case, errors are less.
I'm saying that in that case, the capacitor we are using is impulse voltage capacitor, which has slow charging and fast discharging. That also matters, sir.
Impulse
voltage capacitor we are using, sir. High slow charging and high discharging for getting a testing the object, sir.
You are talking about capacitor inside the impulse generator.
Yes, sir. Yes.
That you can consider in the actual estimation itself. But whenever you change the test object, its capacitance will be different. Therefore, you cannot accurately estimate just by measuring the charge of the capacitor. So, predicting depends on case to case basis. So, this actually inside the impulse generator, whatever capacitances are there, that can be readily taken into account. But what about the new test object which comes? Always some new test object comes, therefore its capacitance is unknown. That is why error will come. But impulse generator capacitors etc. we already take into account normally. Yeah. Any other question? Yeah, it will change a little bit. But the voltage of the diodes and then this capacitor, ammeter, to which it can be subjected to the maximum current value is so small that the resistor is normally small.
What about, sir, if we don't use the protecting that inner diode protection and resistor in place of that, if we use the fuse in series with measuring instrument?
No. For impulse voltages, fuse is not a good option because fuse works based on what? Not breakdown heat generation, right? I square R. So the heat generated is it is an impulse current, very short duration heat is generated. It is not adequate to, it may not be adequate to break also. That's why fuse is not a good option.
I'm not saying about the melting of metal type fuse. I'm saying that gas type of fuse.
So then you are talking about that only, protective device. Okay, this whatever I have spoken, that is gas discharge type only. Series?
Yes, sir. Act as a fuse to limit high current to limit, because the measuring instrument takes a very low current, microampere or milliampere, something like that.
No. If you use series, there can still be problem. The reason is, see, we have to provide alternate path to the ground. Okay. By connecting the Zener diode at the position shown, I am providing an alternate path to the ground to the lower capacitor plate. Okay. Whatever charges are there, they instead of going through this diode or this system, they will simply flow through this breakdown channel when the voltage exceeds. When the voltage exceeds, right? But otherwise, if you keep in the series itself, then you are not providing an alternate channel. So through the same path, it will break. So excessive current will go at the instant of breakdown itself to the diodes. So how do you protect it?
I am saying that in place of the second one resistor, you put a second one resistor in series with the capacitor and two anti-parallel diode. In place of that, if you connect a fuse, then if the case subject if the case subject suddenly fails and high current will flow through the meter, then fuse will suddenly go compressor to protect the measuring instrument.
Actually, when it is connected to the ground, it is bound to discharge the charges, right? So if you are blowing a fuse in series, what will happen now? During that short duration, entire charges would try to escape by arcing at least. So you cannot control. So that charge will definitely go through the diodes only. It will definitely break. So one thing. Yes. Inductance already it is low in these cases. Of course, if you if you have to analyze any circuit, resistor, inductor, and capacitor, all these three things have to be considered. This is basically a capacitive system, and if you add inductance, it will complicate the system. Not only that, its impedance will change, but two storage sources, and they store the energy in different phases is difficult. That energy transfer between those two will occur. It will complicate the problem, and sources possibility of resonance will also be there. Resonance may not occur at power frequency, but if there are some harmonics, then what will happen? At a different frequency, impedance may match, right? Or during the breakdown, the frequency components are high. During the breakdown, the frequency components are high. Then what will happen? The impedance, inductive impedance J omega L, right? It will increase. Okay, so we have to be careful. We should not introduce inductance here.
Okay. But sir, the test object can be anything, right?
It can be anything. We cannot control the test object, but normally test object is connected in such a way that it is basically a capacitance. The high voltage testing will be like that, it may be a motor but having several turns, but the test that we conduct is one terminal will be on the winding, another terminal will be on the casing, so that our interest is to test whether there is any problem with the structural insulation, right? So that's how it is connected. You can assume it as a capacitor test object. But it does have, stray valves, stray inductances, resistances. It does have.
Okay. Thank you.
Okay, welcome. So any other questions?
Sir, you said that we are measuring for half a cycle, for half cycle and getting an average. Where we are connected to two diode, anti-parallel diode.
See how the negative half cycle current will go.
So we are not measuring the negative half cycle current, sir. We are measuring the for getting a peak voltage. We are measuring the positive half cycle current only.
No. It will not work. It will not work. Current should be, continuous, right? See, suppose on the plate, okay, on the plate, negative charges are induced. How this will happen?
Negative charges will flow to the potential, sir.
If on the plate positive charges have to be induced in the next cycle, how this will happen? Already there are negative charges. Okay. So how the positive charge will induce? How the plate suddenly becomes polarized in a different way?
Alternatively, positive and negative charges are changing, sir. We have mainly considered negative charges and measuring by negative charges we can proceed, sir.
But on the plate, how it will come? How it will happen? There should be continuity of charges, right? Going and coming. See, charge cannot be created by the plate itself. Okay then, we'll continue tomorrow.